Hi, everybody. Our plan here for today, um, I think you guys have course selection to get back from break. So I want to take just a minute for the juniors room, and talk about available courses for next year. So there's basically 5 options to count as a math credit. And I'll kind of sort them from like most rigorous to, or least rigorous to most rigorous. So there's personal finance and math apps. Those are each 1 semester courses that pair together. Accounting 1 and 2 count as math credits for Notre Dame anyway. There's, go ahead. Yep. There's IBSL, which I think the prerequisite from this class is an A- or better both semesters. There's AP Statistics, which I think the prereq is B+ or better from Honors Algebra 2. If you took regular, you have to talk to Ms. Garcia specifically about that. And then the last one is AP Calculus, which from this class you need like a hard A both semesters. And probably be looking for an exam A as well. Is you need a recommendation from me for that course, so you have to come be talking to me, and that's kind of what I'd be looking for to move from this class to that, since it's a pretty big jump. Any questions about the course options, like what they are, what it's about? Yeah, Alex?
I know like there's like the new AP whatever doesn't that count for it?
You know, I'm not positive, as it's the first year the course would be running next year, and I forgot all about that one. I would ask Miss Garcia, if she's the department chair, I think would know that for sure. Yeah, it's an excellent question. I don't have a good answer to it. Anybody else?
You said A- for IBS.
Yeah, that's what we're looking for. Okay. And again, if it gets closer and you guys have more specific questions or individual questions, you can surely come talk to me. I'd be happy to give you my advice or talk you through the options again, whatever. Also worth letting you know that I put those options into an announcement on the minor name page. So if you're like, what were those things again? Yes.
When are we doing this?
I think when you come back from winter break. I think the week you come back is when we start doing that. Okay. All right, so today we're going to get into back to talking about polynomials, and we're going to lead off with polynomial division. And hopefully you remember from your Algebra 2 class that there was like 2 ways to do this polynomial division. Does anybody remember one of the 2 ways?
Long division and synthetic.
Yeah, that's great. Long division and synthetic division are the 2 ways. Now, last year in your Algebra 2 class, you should have done a pretty good job of developing these two skills. Not so good as that I would expect you to have mastery without a review, but one of these were like we do a couple of examples and you're kind of get back up to speed rather quickly, okay? So the idea here is like if I have some like polynomial f of x divided by some other polynomial h of x, we can write that in a form like this, or just some vocab. That guy's your dividend, h is our divisor, this part is called our quotient, and this guy is our remainder. And this works for like all division, right? These are the same terms we used like in grade school. You learned about the division process. So we're just kind of rehashing these same things. Let's grab an example of some long division. So let's say we have this fella here that we're going to do long division on. So we want to start by, like we're going to draw like our division bar or whatever. What part goes on the outside out here? Okay. And what part's going to go under? Yeah, the top, right? Yeah, forgot the x there or something. Okay. Now, this is all good, but there's something that I would do here. I would rewrite something a little bit differently to make my life easier. Does anybody see what to do, Max?
I was take the x2 out of it. Oh wait, no. Yeah. Right.
I'll give you a hint. It has to do with the x squared minus 3.
That's what I meant. Take the x2 out of that problem. That. Oh no.
I think you're confusing synthetic addition with addition. Does anybody remember?
Make it all one.
Is anything missing here? Where's the x term?
No, it's just one.
No, it's not 1x.
One x squared. Oh.
So I'm going to write in if I'm missing any terms, like if any terms are skipped because there aren't any, I want to rewrite those in the correct spot with a 0 there. Now, it's recoverable if I don't do this, if I'm paying really close attention and I make sure that I'm not adding things together that aren't like terms, but it's very easy to make that mistake if you're going quickly. I like to make sure I include the missing terms so that everything lines up and then I don't have to think too hard about what's like terms or not because they all just will line up for me. Everybody okay there?
Wouldn't it be minus 3 after that though?
Oh yeah, it's minus. I'm sorry. Thank you. Thanks. Of course. All right. So then I'm going to ask myself what times x squared gives me 2x cubed. 2x. So I'm going to write that above. Notice I just put the x's above the x's spot, right? And I'm going to distribute that to everything in my divisor. And I'm going to write my answer below. Does everybody feel good there? And then I'm going to subtract down. So when I do that subtraction, I have to remember I'm subtracting the entire polynomial I put there. So what Mr. Kulik likes to do, great Google Drive, thank you, is to distribute that negative through before I make my next step. Is everybody okay with what I did there? And now I'm just going to add down. So 2x cubed minus 2x cubed, that's 0. 4x squared minus 0x squared is still negative 4x squared. 5x plus 6x is 11x. And then I bring this last guy down. So far, so good.
For the negative, is it like, are you always just subtracting? Like, so that's why it's minus 2x.
Because I distributed the negative through, right? These signs need to be opposite on the first one. Then I'm going to ask myself, so I did this once, how do I know if I can still keep going? If the degree of what's left is greater than or equal to the degree of the divisor, you can continue to go. As soon as that stuff that's left is strictly less than the degree of the divisor, you're done. Everybody okay there? So I'm going to ask myself then, what times x squared gives me negative 4x squared? That is negative 4. Let's get a different color here. So negative 4. Just like before, I'll distribute that across. And then we'll subtract the whole thing down. But how does Mr. Gulick like to do this? He likes to distribute the negative through, so the signs will be natural. Now we just go straight down. Negative 4x squared plus 4x squared is 0. 11x plus 0x is 11x. 1 minus 12 is negative 11. And now the degree of my what's left is strictly less than the degree of my divisor. So my remainder then would be 11x minus 11. Okay. So do you feel okay there? So the way that I'm going to write my final answer then is I'm going to write this division problem is equal to my quotient, which is the 2x minus 4, there, plus my remainder, which is 11x minus 11, over my divisor, which is x squared minus 3. That's the way I want you to be able to write your final answer. Does that feel familiar? You guys remember doing this? That's good. This month's the next thing we need to talk about here. Okay, so the next piece is called the remainder theorem. Where I'll steal that from Jeepers Creepers. they like redo all these Adobe programs like every 2 minutes, and like for whatever reason somebody thought it would be like a really great idea to not be able to scroll with a touch screen on through Acrobat anymore.
That make way too much sense.
Yeah, right? Like why would
Especially for Adobe.
why would I not want to do that?
That make way too much sense, especially for Adobe.
Yeah.
The arguably worst company.
Next thing we'll talk about is the remainder theorem. So the remainder theorem says if a polynomial f of x is divided by x minus k, then I can compute the remainder of that division problem by just evaluating f of k. So we're going to then use that remainder theorem to find f of 2 for the polynomial 2x squared minus 5x plus 4. So f of 2 we know is the same thing as the remainder for our f of x divided by x minus 2. That's the guy we're looking for, is whatever that remainder is. So let's go ahead and do this. We'll do this doing long division also. Just for the one more round of practice. So what can I multiply x by to get 2x squared? 2x.
But isn't the x squared bigger than the degree we have though?
Right, the leftovers are greater, so that means we can go.
I thought it like if it has to be like equal to the one left.
But greater than or equal to is means you can still go. If it's strictly less than you stop.
I should find x minus 2.
From the theorem. The theorem says the remainder, when I divide it by x minus k, will be the same as f of k. So my k is 2, so I'm going to be dividing by x minus 2. Okay? Subtract down. We can confirm this directly, right? So this should give us the same thing as if we compute f of 2 this way. So I have 8 minus 10 plus 4 That's also positive 2. It does seem like that theorem does do what it says it's going to. Now, the obvious question for you guys is, why in the heck would I bother doing polynomial division to figure out just what something evaluates to, right? The answer is you wouldn't. This is just a step along the way to building the synthetic division process and justifying why that's going to work and do what we say it's going to. So this is like a building block on the way to something better. Is everybody okay there? So the next piece is the factor theorem. And the factor theorem says that polynomial f of x has the factor x minus k if and only if f of k is 0. So notice this is an if and only if statement. What does that mean? It means you can read it both forwards and backwards. So it means that if x minus k is a factor, then f of k is 0. And if f of k is 0, then x minus k is a factor. So it works in both directions. So then our next example, we're just going to use our factor theorem to show that x plus 3 is a factor of the polynomial 6x cubed plus 25x squared plus 16x minus 15. So again, we'll use long division here just to get a handle on this. So when doing this, what should our remainder be? Should be 0, right? It says show that x plus 3 is a factor. If it's a factor, then the remainder must be 0, right? For example, 2 is a factor of 8. Because 8 divided by 2 is exactly 4. 3 is not a factor of 8, though, because 8 divided by 3 is 2 remainder 2. Everybody okay with that? Or I'm sorry, 2 remainder 2. Everybody's okay with that? Okay. So, what times x gives me 6x cubed? 6x squared. And then we distribute over. I'm going to stop drawing all these little arrows and stuff. Is that okay with everybody? And I'm going to stop drawing in the distributing the negative. I'm just going to write it out front and then do the distributing in my head. Is that okay with everybody? All right, so that gives us 7x squared, and then we'll bring the rest of our stuff down. Technically speaking, I don't need to bring the negative 15 down at that step, but I like to do it anyways, because sometimes I just forget about them if I don't bring them down every time. Next step, what multiplies x to give us 7x squared? 7x. And then degree is still greater than or equal to, so I need to keep going. So what times x gives me negative 15x, negative 5, distribute through, subtract down, I get remainder 0. And that's what I needed to show that it's a factor, right? Because this implies that f of negative 3 is equal to 0, which implies x plus 3 is a factor. Yes,
So we're gonna be like labeling these problems like by these theorems?
no. Just trying to explain to you how we would use them. Right? Most of the homework is going to be like, do this synthetic division, do this polynomial division, or then we'll get to the type of example of the type of problem you'd be doing in your work. But not this. Okay. So just to kind of illustrate what's happening here, we have 6x cubed plus 25x squared plus 16x minus 15. And we divided this by x plus 3, and we got the quotient of 6x squared plus 7x minus 5, right? And because we have a remainder 0, I don't have to write anything else after that. Does that feel okay, everybody? Now, these two things are equal, right? If I multiply both sides by x plus 3, that's going to eliminate the fraction on the right-hand side. And what do I have here? Like a partial factorization of the original, right? Is everybody okay with what we just observed? So we're kind of circling a method, a new method for factoring that we can add to our factor tree that we developed in the last lesson. We haven't quite got there, but we're rounding our way to it. So, what this does now is it should give us an idea that, hey, we should try to streamline this division process if this division process is going to be really important to us in factoring later on, right? We would like that process to be a little bit more time intensive or less time intensive and a little less paper intensive. So that process is synthetic division, which is essentially just our substitution process, right? So if I took that same problem we want to create this as a synthetic division problem. And I start with our little synthetic division setup. What number goes on the outside here? Not x plus. Nope. Nope. It's negative 3. We have to take the divisor, set it equal to 0, and that solution goes out here. What numbers go along here?
6, 25, 16, 15.
The coefficients from our polynomial. What do we have to be really careful about when we when we do that.
Spacing.
Spacing, sure, but something else, something that doesn't have to do with neatness. I have to be really careful about skipped terms, right? If I was missing, say, the X term, what do I have to make sure I include?
0.
A 0. If you do not do that, it is not recoverable that you can still get the correct answer if you're paying attention. It'll just be wrong. There's no way to like figure it out halfway through that you're missing the 0 without having to like erase and put the 0 back in and continue properly. Is everybody okay? So that's our setup. What's the first step in this synthetic division process? Actually, pause. I'll come back to that. Before we do that, when can I do synthetic? When can I do synthetic division? It doesn't work every time for every division problem. Only certain division problems. What's that?
Like one's like a full part.
What's it?
When it has like all like x to the third, x squared, x, and like that.
Nope.
When the divisor is a binomial.
Okay. When the divisor is a binomial, kind of. It's more to it than that, but you're on the right track. The divisor is the key.
And it has to be like x plus.
Okay.
something.
Good. So it has to have leading coefficient 1 and degree 1. That's your condition. That's when you can do synthetic division. The divisor must have leading coefficient of 1 and degree 1. If you don't have those conditions, you cannot do, well, you should not do synthetic division. If the leading coefficient isn't 1, you can kind of like fake it, but you have to do some adjustments. It is kind of complicated. But if the degree isn't 1, it just like flat out doesn't, the process just doesn't work for us. Everybody okay? Okay. Now we should talk about the first step. The first step is to we bring down the first number, and then we multiply, and then write the answer here, and then add down. Everybody's okay with that? Okay. And then we multiply, write the number here, and add down. Multiply, write the number here, add down. Everybody feel okay there? Now these numbers at the bottom of our synthetic division problem mean something, right? We start naming them from the number on the farthest right. It's like the only time we go from right to left instead of left to right. This number on the far right is the remainder. This number is the constant term for the quotient. This number is the x coefficient. This number would be the x squared coefficient. And they just kind of keep going on. You know, every number you have, you pick up one more degree. Is everybody okay there? So this is really a lovely time-efficient process compared to long division, right? It takes up less space. It's way simpler computationally and structurally. Gives you all the same information. The hitch is, doesn't work for every problem. It only works for certain problems. The good news is, the majority of the problems we need to do this on it's gonna work. All right. Feel so far so good? Go scroll down because I didn't get enough printouts from this. Missing some pages. Okay. Yes, go ahead. Okay. All right. So what we're looking to do now is to build out a factoring process out of this synthetic division, right? We see that if I can identify a factor, it's going to give me a 0 remainder when I do the synthetic division. And once I have the factor and the quotient, I can put together a partial factoring of my polynomial, right? The hitch is, how do I find this? Once I have a factor to start, confirming it's a factor and doing the factorization, that's now going to be easy. I can do the synthetic division on it. But finding that first factor to get this process kick-started, that's going to be a little bit of a chore. The main tool we have for that is called the rational zeros theorem. So the rational zeros theorem says, if our polynomial has a rational zero, then that zero is of the form plus or minus some factor of the constant term divided by factor of the leading coefficient. So we can use this to identify potential candidates for that initial synthetic, or for finding that initial factor, right? Now, this can be kind of a mixed bag in terms of how effective it is. So let's steal this example problem. Oh, come now. I swear I did this. Okay. So if I want to make a list for my possible rational zeros, I'm going to start by identifying my factors of the constant term. What are my factors of 4? That's not all of them. 1, 2, and 4. Those are all the numbers that divide 4 evenly, right? Okay. And then I need my factors of the leading coefficient, which is 3. 1 and 3. Is okay here? So I'm going to have plus or minus, constant over leading coefficient, and then constant over leading coefficient. And then plus or minus, constant over leading coefficient, constant over leading coefficient, constant over leading coefficient, and then constant over leading coefficient. For this problem, I have 12 candidates for a synthetic division, right? Now, that's still kind of a lot if I'm guessing blindly through this, but it was a heck of a lot better than before when I had infinitely many, right? If I can take infinite down to finite, that's a heck of a first step, even if the finite number is not teeny tiny. Does everybody feel okay there? All right, where do we go next from this? Okay, so time for another theorem. So this list is still quite long, right? There's a second theorem that will allow us, when we're checking blindly, on occasion, we'll be able to cross off multiple answers, which is great. We love when we can do that. So here's our theorem that allow us to do that. All right, let me grab that guy. So this theorem says if f of x is a polynomial with a positive leading coefficient, and we divide by some value k using synthetic division, if k is a greater than or equal to 0, and every number in the bottom line is non-negative, so positive or 0, then k is an upper bound for all the real zeros of f. What that would mean is I could cross out, if I saw this happen for, say, like when I was doing this for positive 1, right? If I saw that all the bottom line of my synthetic division was all positive or 0, I could cross out 1 and 2 and 4 and 4/3, the positive versions of them. Because 1 would be an upper bound. That means that there are no zeros bigger than 1. So it allows me to kind of get multiple for the price of 1. Similarly, if I do that same division by k, and every number on the bottom line alternates from non-positive to non-negative to non-positive, then k is a lower bound. So again, if I did that for -1, it would also allow me to discard -2, -4, and -4/3 if I observe this alternating happening at the bottom. Everybody okay there? So let's take a look at this polynomial. So I'm going to start by identifying the possible rational zeros. So I have the factors of 15 divided by the factors of 6. Our factors of 15 are 1, 3, 5, and 15. Our factors of 6 are 1, 2, 3, and 6. So I'm going to have and then I have over 3. Now, here I'd have plus or minus 3 over 3, but I'm not going to write that down because it's the same thing as 1. 5 over 3, and then I have plus or minus 15 over 3. Which again, I'm not going to write down because that's the same as 5. Now, 3 over 6 is the same as 1/2. I'm not going to write that down. And 15 over 6 is the same as 15 over 2. Not going to write that down. Is everybody okay with the list of possible rational zeros I came up with here? So there's kind of naively 16, but really only, I should say, 32. Because there's plus or minuses on all of them. But I can reduce that down to 20. Still kind of a crumbly long list though, right? All right, so let's suppose that I picked -5 as my check. Oh, yeah. Okay. So -5 doesn't work. So I can eliminate the -5, right? Would you agree? But this is a negative value that I divided by. And I notice that the numbers at the bottom alternate in sign. So I can also eliminate anything that's less than -5 on my list. So I can get rid of -7.5 and -15. So that one synthetic division allowed me to get rid of 3 possibilities. Okay with that? So when I'm doing this, I want to be on the lookout for these sorts of opportunities. Next, I'll try, it said to try 4. So again, I'll do the same kind of thing. 49 is 196. So that's 212, 848, so that's 833. And again, this is a positive value, and below I got all non-negatives, greater than or equal to 0. So 4 didn't work. Well, 4 wasn't on my list, so oh well. But since these were all positives. I can also discard anything on my list that was greater than 4. So I can get rid of positive 5. The 5's gone altogether. I can get rid of 15 over 2. The 15 over 2s are gone altogether. And positive 15. So the 15s are gone altogether. Is everybody okay with how I can use this theorem when I'm checking for zeros to kind of get a little bit more bang for my buck, so to speak? Now the problem says show that every real zero, blah, blah, blah. So here you would just be like, okay, positive, negative, positive, negative. So negative 5 is a lower bound. Here you have positive, 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 positive. So you'd say 4 is a upper bound. In terms of like, all you really need to do is this synthetic division. I'm trying to show you like how this would be used. How is this useful to you? When I was a student, this was quite useful because you know what I didn't have? A graphing calculator to like look at the picture and have a good idea of where to start. So this was mostly a wild goose hunt for me, and these things were super helpful. All right. I think we have one more example or something, and then, yeah, there we go. That'll be my last guy right there. Right? Yeah, good. Okay. Let's grab that example, and we're going to do this the way Mr. Kulik would have done it when he was your age. So we're going to get in the time machine and go back 30 years or something when I was sitting in that desk. All right. So we'd start by looking at and trying to identify how many solutions we have. We're looking for at least, we have at most 3, right? Because the degree is 3. Now we could have some repeats or whatever, where we might have less than 3, but that's okay. We have at most 3 zeros. So far, so good. Now I'm going to construct my list of possible rational zeros. So my factors of 30, oh, Boise, that's a lot of those. And then my factors of 6, there's a lot of those. Yuckarooskies, guys, this is going to be a real bummer. And I'm going to skip 2 over 2 because we already got it on our list. I'm going to skip 6 over 2 and 10 over 2 because we already have them on our list. I'm going to skip 30 over 2. We already have it on our list. I'm going to skip 3 over 3. We already have it on our list. Skip 6 over 3. We already have it on our list. Skip 15 over 3, we already have it on our list, and skip 10 over 3, we already have it on our list. Skip 2 over 6, we already have it on our list. Skip 3 over 6, already have it on our list. Skip 6 over 6, we already have it on our list. Skip 10 over 6, we already have it on our list. 15 over 6 and 30 over 6 are already on our list. So that's our complete list. Notice that, how do I know when I can skip these? Anytime they can reduce, really. If I can reduce the fraction, I can skip it because it's going to be somewhere else already. So again, you're right. I'm just making it even simpler where like I don't even have to check to see if it's on my list somewhere. As soon as I can see that it can reduce, I've already got it somewhere else, so. All right, time to start synthetically dividing. I don't have a graphing calculator in 1996 when I would have been sitting in a classroom doing this. So I'm just going to start arbitrarily. Which one do you think Mr. Kulik would start with? Which number is going to be the easiest one to synthetic divide with? 1. I agree. Yeah, 10's not a bad choice either, but my experience would have told me the big ones are rarely used. And the little ones, sometimes you can get lucky and like knock out 10 other ones at the one shot with one of those upper bound theorems. So I like kind of the smaller ones. 1, and then I have 623, negative 83, and negative 30. All right, and just start ripping and roaring. That doesn't help me. It's not a 0, and it's not a upper lower bound. That's a bummer. What I see here, it doesn't work, but oh, yeah, didn't work. It doesn't give me nothing. All right, I'm gonna go to 2 now, I guess. Again, we'll talk about how to use the graphing calculator to speed this up, but I want to get you a little feel for what like math in 1996 would have looked like. Doesn't work. Who wants to grow up in the 90s here with me? I don't hear all you guys being like, ooh, me, Mr. Kulik. It was a better time, guys. Uh, 123. Enough to see that it's not going to work. And at this point, Mr. Kulik's like, maybe I'm going to try the halves because I don't like getting too big. I don't know, 4 or 6 might, like some of those might work still, but I'm frustrated, or 5 and 6. I'm frustrated. I'm going to go to do the halves now. Still haven't found like a lower bound or an upper bound yet. But the halves are usually pretty easy to work with. And that still didn't help me, but I like the way that looked. I have optimism about the negative 1/2 that that's going to do it for me. Yeah, didn't work. All right, well, thirds won't be bad with the 6 to start. If I'm getting a fraction on the first one, though, I usually bag it, try something else. And that's not going to work. It's already area fraction. Ooh. All right, that did it. Yes. All right. So what that tells me then is that 6x cubed plus 23x squared minus 83 minus 30 is going to equal x plus 1/3 times remainder constant x squared, 6x squared plus 21x minus 90. Everybody feel okay?
Yeah.
This is quadratic. I'm hoping that I'll be able to factor this using our factoring tree methods. I would go factoring tree, but you could use the quadratic formula here since we're in the end looking for zeros, but if I asked you to factor it, it's a lot harder to reconstruct the factors. I noticed the first thing I check for is a greatest common factor. I see a greatest common factor of 3 here. And I can go and like push that 3 back through here and make that a little cleaner up. Now to factor this, the leading it is in the quadratic form, like it's quadratic literally. The leading coefficient isn't 1, so I need to do that long factor where I find like the two numbers that multiply to give me 2 times negative 30, and then add to give me 7. What are they? Other way around. So what that does is allows me to rewrite the 7x as 12x minus 5x, or plus a negative, and make my two groups. From the first group I can take out a 2x, and from the second group I can take out a negative 5. X plus 6 is in common to both. So if I take that out, I'm left with 2x minus 5. So I have my fully factored form, 3x plus 1 times x plus 6 times 2x minus 5. So if I set these all equal to 0, then I get 3 solutions, negative 1/3, negative 6, and positive 5x. Now, how can you speed this process up? Use the calculator. How are you going to use the calculator? You're going to graph the polynomial that you're trying to factor and look at the x-intercepts, the zeros, to help you choose which numbers to start, right? You guys remember doing that? But this is what it was like when I was in your class doing the same thing. And you got real good at synthetic division real fast because you had to do, like sometimes 20 or 30 of them in a problem. We didn't assign any of them because sometimes it just do it at lunch. You were a hero when you found it, though. Everyone's like, oh, 7 halves, great. Let me go straight skip to that one. So at this point, you guys should be able to do up through 35. Okay. So that'll be Sundays. Homework will be 1 through 35, basically. We'll finish the rest of this stuff next time. What haven't we had yet?
Homework quiz.
What might be something I wanna do before we go on winter break?
Homework
I
quiz!
wonder. I'm taking my 3S.
Yes. Just throwing that out there is like, maybe that's gonna happen.